Hello everyone. So now we are going to discuss the third, fourth, and fifth vacation knapsack 1 and 2 problems from the Atcoder DP contest. 26 problems we have. So the third one, C vacation. So here Taru's summer vacation starts tomorrow and he has to decide to make plans for it now. Vacation consists of n days. For each one I from 1 to n, he can choose three activities, either A, B, or C. But there is a condition that as Taro get bored easily, he cannot do the same activities for more than 2 or more consecutive days. This means that two uh, consecutive days must not have same vacation. If there is A, then there must come B or C. If there is B, next will be either C or A. No, two consecutive numbers must not be the same. Only this. Find the maximum total points of happiness that Taro gains. Okay, so after choosing some activity, he will get some happiness. Okay, after swimming A, he will get A point of happiness. After B, B1 point of happiness, C1. So let's say on one day one, he chose to go for activity B. So he will get B1 happiness. For day two, he chose C2, so C2 happiness. For day N, he went for AN, so AN happiness. Okay. So try to solve this problem on your own first. Okay. So try to think of what can we do. So we have N vacation days. He can choose any activity. The condition is no 2 days must be same. And how we are getting these happiness values from the activity we are choosing. I'm going to maximize this activity. Okay, this happiness. Okay. So let me just discuss my method. The method I do. Simple like include, exclude. No, it won't be exclude, include, but it is very similar. So I input the n three vectors of happiness A, B, C. If n is equal to 1, I simply give out the answer, just max of n, pick one. Okay, just filter out the edge case very easily. Then I kept the answer to int min. Then I solve for the first time. If I am choosing A, then how will I solve it? Then the first day I'm choosing B, I'm choosing C. Then what will happen? Okay, how I define the recursive function is first the index. This last is what is the last. What is the activity I did on last day? Let's say yesterday I did A. I can't do A today. Okay. So it will be helpful there. Last is not equal to 1, then we can do so. Last not equal to 2, then we can do this. Not equal to 3. For A, B, C, I kept 1, 2, 3. Okay. So I don't understand this part. And why I have kept this first day separate? Because on the first day we can have three choices. We can either go for A, B, C. But on the next day, on day 2, let's say we select day 1 as A. So on day 2 we can only go for B, C. We can't go for A. So on the each day except day 1, we have only two choices. Try to understand this part. This is very important. Like just think this part. On the day 1 we can choose any activity A, B, C. But on day 2 we can't choose any three. We must see that on the last day, if there was B, we have to select A and C. If on day 2 it was C, then day 3 must be A or B. If on day 3 it's A, then B or C. No, that's why the choices are only two choices. So that's why I kept the first one as separate and this function for solving it further. So if last is not equal to 1, simply think of A, not equal to A, then the happiness of A plus recursive function. If it is not equal to B, then take the happiness of B and recursive function. If not equal to 3, recursive function and return the DP. Just try to think of this part, you will be able to solve it easily. Okay. So the next problem is knapsack problem, standard, include exclude principle. We have n items, 1 to n. Each item has some weight and value. Okay. And Taru has decided to choose some of the n items and carry them in knapsack. The capacity of knapsack is W, means only total weights at most W can be taken. Okay, there is a constraint on weight, so we can take at most W and find the maximum serve values. So we have to maximize the values and there is a constraint on weights. Okay, it's a very standard problem. I won't discuss it further. We use the concept of include and exclude. Simply share my code. Okay. For this, I define the weight and value vectors I taken in as input. TP vector, I called on the recursive function on knapsack. We have index, we have current sum, we have total index, weight allowed, and weight value vector and DP vector. Okay. So here we are excluding it. If we are excluding it, index plus 1, there is no addition in sum. Okay, and the index is same. And if we are including it, maximum value of val exclude comma include. Okay, and when we are including it, we will take the value. Okay, value plus knapsack, index plus 1, and then we are doing weight plus because we have taken that item. Okay, just think of this part, you will spend some time on it. Just spend some time. This is very simple. Include and exclude principle. Okay, since we are excluding here, we are neither adding the sum or taking the value its value, but we are including here, so we are taking it value plus this. Okay, and this is the base case hour, and does the dp not equal to 1, return dp. Okay, and since we have a constraint on weight, so we'll check this first. If current sum, the sum we are currently plus the weight of the current value of index is less than equal to 1 w, like total weight which is allowed, then just go for it. If not, it's not allowed. Okay, now we try to think of the like a time complexity. So our index can up to go up to 100 values. Okay, and our total allowed weight is 10 power 5. So our states are basically index, it will take 100 values, and current sum it can take 5 values. So total will be big of O into and 100 into number 5, number 7. Okay, so that will be time complexity, the multiplication of big of n into w, which will be 10 power 7. So we can solve it, it's solvable in the method we did. By the next knapsack 2, there is a problem that we have our weight constraint increased. From 10 to 5, it went to 10 to power 9. So this problem, if we apply the same concept, we do in big of n into w, 10 to power 7, here it will go 10 to power 11. So we can't use the same concept. Are you getting this part? If you try to apply the same concept of include and exclude, we can't do the same in this problem. We need to change our method. It was a trickier. I also use Google and everything to get the answer. But let's just discuss the solution I got. Okay, I have to open the file. I've deleted open file. So here what we have to do, we have to define ij, dp I and v. We have to get the minimum total weight to get value exact value v for the taking using first I items. Okay, so we are taking first some I items, and we need to generate value v from that. And what is the minimum total weight required? Okay, so here we are using dp on the value part. Earlier we are using dp on the weight, current sum. This is the weight part. Here we are changing our concept entire way. We are using the dp on value part. So that's the change. Okay, and the result of thing will change a bit. We are using the same concept of here we are excluding, here rest here we are including. Okay, so exclude include concept will be there, but the part is different. Is there we were using dp on weight, here we are using dp on the value. Okay, and we are trying to get the minimum total weights required to generate that value using the certain first some I items. Okay, and what is the max value? Basically, we added all the values in the value vector, all the values, we get the max value. Okay, and then we created this loop from val 0 to max value. So what are the possible values we can get? Max value. So let's say if we got some, it was solvable. Let's say for max value, we got weight is equal to w by 2. Okay, w by 2. W by 2 is less than w. Okay, so the answer will be max value. We will get the answer max value. We are trying to generate the max value from here. Okay, so that's the part. Rest of the thing is the same here. Just include exclude principle, and the base case we have here is okay. So if there is no value to generate, value target is 0, there is no need for weight, take any weight. Weight will be 0. Okay, so that's the method. Just try to go over this. Okay, take some time. This problem is very interesting. Okay then. Bye bye. See you on another day.